Hello, everyone. Welcome to our demo presentation of CRC4EVER, Cyclic Redundancy Check for Enhanced Verification and Efficient Routing. This work is a collaboration between researchers from multiple institutions. We represent institutions including the Federal University of Espírito Santo, Telefonica Research, the Federal Institute of Espírito Santo, and the University of Campinas. This presentation is part of a SIGCOMM 2025 here in beautiful Coimbra. Let's dive in. Let's begin by understanding the motivation behind CRC4EVER. In today's networks, endpoints have very limited visibility into the paths their packets take, and virtually no control beyond just setting the destination address. The Path-Aware Networking Research Group, or PANRG, is working to change that. They aim to bring path awareness into protocol design by enabling three core capabilities. First, the delivery of path information. Second, allowing endpoints to select paths. And third, verifying that packets actually followed the intended paths. But here's the challenge. While path selection and delivery are already hard enough, path verification is especially tricky because most existing techniques rely on cryptographic operations, which are not only heavyweight, but also difficult to implement efficiently in programmable switches. And that's exactly where CRC4EVER comes in. Let's now take a closer look at the CRC4EVER design approach using the residue number system, or RNS. In this topology, each network node is assigned a unique node ID, which corresponds to an irreducible polynomial. These polynomials play a fundamental role in enabling path encoding and decoding using modular arithmetic. We start from the source, represented by this edge node, and assign the first irreducible polynomial to the initial node. As we progress, each subsequent node along the path is assigned a different irreducible polynomial, ensuring that the identifiers are both unique, a key requirement to maintain the mathematical guarantees of the Chinese remainder theorem. Here we show how to calculate the root ID using the Chinese remainder theorem. For the selected path, highlighted in blue, we consider three nodes. At each node, the router will compute route ID mod node ID to find the correct port ID. Using the Chinese remainder theorem, we combine all these values into a single number, the root ID. The route ID is 100101111, which will be carried inside the packet as it moves through the network. This allows each switch to know where to forward the packet, using only a simple modulo operation. This mathematical structure ensures that, for any given path, there is one unique root ID that represents it. Now, to verify that the packet followed the correct path, we use the uniqueness of each node ID, port ID pair, which is a native property of this routing system. Based on that, we propose a path signature. This signature is created by chaining CRC-based hash operations from each node along the path. More specifically, we compute the proof of transit, or POT, at each hop using the formula below. This chaining mechanism allows every node to contribute to the path signature, and any mismatch means the path was altered, making verification both lightweight and reliable. The conceptual design of CRC4EVER. It illustrates how the root ID and proof of transit metadata are inserted, processed at each hop, and finally verified at the destination. Each switch uses the route ID to forward the packet and updates the POT using CRC operations. Using the blue path at this example shows how the path is processed in CRC4EVER. The edge node is responsible for computing and inserting the root ID and the initial POT into the packet header. At the first core switch, the data plane logic begins by extracting the root ID and the previous pot. The switch performs a simple calculation. It uses the modulo operation between the root ID and its own node ID to find the output port. Next, the packet is recirculated back to the ingress pipeline, where the switch updates the proof of transit. It applies a CRC32 hash over the current node ID, port ID, and the incoming POT value. The resulting POT confirms that the packet has visited this node, and the process continues to the next hop. Now at second core switch, the packet continues along the blue path. Calculates this, give the port ID, used to forward the packet to the next hop. Then, the packet is recirculated back to ingress for the POT update. The new pot is computed using the CRC32 hash of the current node ID, port ID, and the previous pot. This ensures that the packet's journey is verifiable, and that this switch has contributed to the path signature. At the final core switch, the process is repeated. The switch uses its node ID and the received route ID to compute the output port. After determining the next port, the packet is recirculated once again for POT update. The new proof of transit is calculated using the CRC32 of the current node ID, port ID, and the previous POT. Once the packet reaches the destination edge node, it performs a final verification. The proof of transit is checked to ensure the packet followed the correct path. After verification, the metadata is removed and the packet is cleanly delivered to the destination. This completes the CRC-4EVER forwarding and verifiable process. We begin by demonstrating the loading phase of the CRC-4EVER architecture. The switch is configured with two precompiled pipelines, one for forwarding and another for verification. The topology has already been set up and is now up and running. Once everything is initialized, we proceed to populate the ports and the Tofino match action tables with the required configuration. Next, we show that two physical ports, each connecting the programmable switch to a server, are enabled and operational. On one of the servers, we start a TCP dump session to capture packets and visualize the path verification stack corresponding to the hops through core routers in Path 1, Path 2, and Path 3. Then from the second server, we send one packet per path, triggering the path-aware forwarding and proof-of-transit mechanisms in the switch. Finally, a summary of the captured packets is displayed, showing the packets. Our proof of concept on programmable switches confirms the feasibility of CRC4EVER's design. As future work, we plan to conduct a security analysis to identify and better understand potential attack vectors and enhance robustness. Thank you for watching this demonstration of CRC4EVER. Cyclic Redundancy Check for enhanced verification and efficient routing. We appreciate your attention.